So I had provided one lecture. All of you, I hope, got time to go through it. So I will cover part of it here also, because that was recorded way back. Hopefully, there will be some clarification based on that. So before we proceed, let me also talk about some motivation, because I don't think the motivation was particularly clear in that video as to why we should be should be studying non-time invariant network, or why should we be studying time variant network, right? So given the fact that from now till a bunch of weeks we'll spend on time varying networks, so it's probably instructive to understand what is the motivation behind it. So at the beginning of the class, beginning of the course, I think we had talked about briefly about what is an LTI system, what is a non-LTI system, and so on. And one example that I had given you was that of a multiplier. Let's say this is a box, and this the second arm of the arrow is a part of the box, and let's say this is d of t. If this is x of t, or let's say this is VIT. So this output is VIT times d of t. So then we all agreed that this is not an LTI system. This is a linear system, but this is not a time invariant system. All good. So let's start off with this and see what are the potential applications of this, and then probably it will help us understand what is the motivation behind understanding systems which are not LTI. So for that, I'll have to take you to a bit of architectural level understanding of a radio receiver. Okay, so we use our cell phones all the time. Most of the time we use it for calling, video calling, chatting over video, voice, text, and whatever. But the key thing to note is that it is a wireless interface, right? Firstly, it's a wireless interface, and you have a receiver, and you have a cell phone, which internally has an antenna, which is not visible. It is around the rim of your phone, so it's not visible. But you have an antenna, and this, whenever you are communicating with another cell phone which is not co-located next to you, so that cell phone also has an antenna, and you are transmitting signals which the second cell phone is receiving. And this is not a direct communication, in the sense that there is a tower which sits there. You send it to the tower then sends it to the other cell phone, right? Now let's concentrate on either the transmitter or the receiver. Let me call this a receiver Rx, and this is the transmitter Tx. By the way, this is a nomenclature. Tx is generally referred to as transmitter, Rx is a receiver. Let's concentrate on either the transmitter or receiver. Let's say we concentrate on the receiver, right? So this wavefront that comes in it has a frequency. Obviously, this is an electromagnetic radiation, right? It is an electromagnetic radiation. And are you aware of the size consequences of an antenna with respect to the frequency of an electromagnetic radiation? Right, so size of the antenna has to be of the order of lambda of the radiation that of the wavefront that it is capturing, right? Of that order, which essentially means that if you have a low frequency waveform, lambda is large, which means you need a larger antenna. If you have a high frequency waveform, lambda is small, and you need a smaller antenna. So as it turns out, typically if you know the frequency of the waveform, then lambda is easy to find, right? So lambda is essentially C by F, right? And C is, if I assume free space and all, 3 Newton to the power 8 meter per second. And let's say I take F to be, let's say 1 gigahertz. 1 gigahertz is 10 to the power 9. So this is 3 into 10 power minus 1 meter. Meter. This is per second goes off. Which means this is 0.3 meter. So this is, you can see this is already small or large, depends on the size of the antenna that you are planning to utilize, right? So So this might be okay if you are planning to use a cell phone, but might not be okay if you are planning to use, for example, your handheld device, a watch or something like that, right? So which essentially, and now if I assume that f is not 10.9, f is, let's say, 10 megahertz, then naturally you see the lambda becomes really large. And if I say 10 is, let's say, audio frequency, lambda is f is audio frequency, which is like a kilohertz or lower, then obviously the size of the antenna becomes infeasible to be made in any form or shape, right? So then how do we actually communicate? We do not communicate directly. Basically, we do not necessarily send out the signal that we need to communicate with. We first transfer the signal to a different frequency. We call it a carrier frequency, at which is of some predetermined high frequency, and then we transmit that frequency. Okay, so the first thing we do is convert a low frequency, which is often called a baseband signal, to a high frequency. I just say high frequency signal for the time being. Now, how do I convert anything to a different frequency? Obviously, an LTI system cannot convert a frequency, correct? But maybe, obviously nonlinear systems can, and a time variant system obviously can also convert. For example, the example that we saw here is a time variant system which can convert. So if I take that particular example of a time variant system, you can say that instead of multiplying with any d of t, let me multiply it with cosine omega, let me call it LO. I will let you know why we call it LO in a while. And let's say this I call it as cosine omega BB, that is baseband, times t. So your output will now become cosine omega BBT times cosine omega LOT. And for the timing, assume that omega LO is much greater than omega BB. Okay. So this I can break it down into cosine omega BB as omega LOT. Okay. So what can I infer from here? I can infer two things. One, obviously, is the fact that this guy is of much higher frequency than omega BB. This is also at higher frequency at omega BB because, if omega LO minus omega LO is much greater than omega BB, this is also at pretty high frequency, right? But the key thing to note is that if the input signal had some information, let's say VP cosine omega BB, so I'm going to have the same thing, that the amplitude information VP is still getting transformed into a different frequency, but now this frequency is controllable by the user, that is me, and I can set this frequency to any value so that it is feasible for my antenna to transmit and receive, right? And this cannot be possible unless you have a mixing. This is called a mixing operation, which is a time variant operation. Okay. So this now a definition, omega LO is, this LO stands for local oscillator. The reason it is called a local oscillator is because all your cell phones or all transmitters or receivers has a inbuilt oscillator that comes along with the hardware. It's locally there in your inside your radio. Okay, and that's hence and it's an oscillator because ultimately it has to provide a sinusoid or cosinusoid, some sort of oscillation. It's an oscillator, and it is there locally. That's why it's called local oscillator. The reason it is distinguished from other frequency components is because obviously omega BB stands for baseband, right? But when you are, this is by the way, the transmitter side of the picture, but when you are receiving, when you are receiving the same thing, so this is transmitter. When you are receiving, the input is again, let's say cosine omega BB plus omega LOT. I'm only showing one part of the receiver. In the negative, this will, the other side should also be there, but let's consider it only on this one. I can multiply again this with again a same local oscillator frequency, which is inside your cell phone, right? So this is inside the cell phone. And then here I get VP cosine omega BB, and I get VP cosine 2 omega LO plus omega BB, 1 by 2 times, right? And then you kind of see that you have gotten back the original, but you have gotten a high frequency signal also. But now I know that the difference between omega BB and omega LO is chosen to be much higher, right? Which means, and 2 omega LO is obviously much higher. So which means that I can maybe put a low pass filter and knock off this 2 omega LO term, and I can only have the omega BB term, and I restore the signal of interest, right? So at a very 10,000 feet level, this is what a radio does. Okay, but this is not the RF course. The part that I want you to focus on is that none of this could have been done if we didn't have a multiplier, right? So a multiplier is central to this operation, and a multiplier is a time varying operation. It's not a time invariant operation, right? So that is motivation number one, right? Why we should study, because without this, none of this mobile revolution is possible. Okay. The second thing maybe that is that you should readily appreciate is the fact that we do everything in digitally. All the processing is done in digitally. All the machine learning, intelligence, everything is done in digital. Now the signal after you have received, right? So let's say you have received this. Why are the, where did all the colors go? Yes.
It's also not easy to have this omega BB plus omega LO signal.
One second. Okay, so yeah, so the point that I was making is omega BB, I mean FBB might be a megahertz and omega LO might be gigahertz. So I mean it is trivial to isolate this, right? There are other issues in radio receiver. We will know in RFIC courses next semester. I will not spend time on that. Okay. So the next thing is the other part that should convince you to spend time on time variant system is the fact that when we go from analog to digital, right? So how do we go from analog to digital? We have analog signals. That is, let's say this is this VP cosine omega t. You have omega BBT. You have gotten from after down this process is called up conversion, down conversion, and all, right? So you have got this baseband signal out. Now you need to digitize it. So how do you digitize it? ADC, right? And what is, so ADC is a block that does everything. But what is the first stage of an ADC? You first have to sample and then digitize, right? So sampling is basically nothing but, you can think of, I am multiplying this with an impulse train. Let's say this is T. So this is an impulse train, summation of delta T minus KTS. And so on. So that at the output, I get samples of VP cosine omega BBT, right? So if the input is a continuous time waveform, the output will be and so on, right? So its envelope will seem like the continuous time analog waveform, but what you are going to observe is the samples. And again, from our basic circuit theory, from basic signal processing courses, we understand that what is the spectrum of this? Impulses. It's also an impulse train, right? F minus K by Ts or KFS. right? Delta of, right? And you have a scaling factor, right? Okay. Uh, so essentially, the thing that this is telling us is this is also you are getting multiples. You are getting a whole bunch of other frequency components also, right? And fact that you are also having a multiplying option also makes this a time varying operation, right? And then you do sample and hold, you hold the waveform, and then you do quantization and a whole bunch of other things. But for the sake of this course, we'll just say we'll stop here and say that okay, it is motivation enough. The fact that the first level digitizer itself will require some sort of sampling operation, which essentially means that we need time varying. We need to understand how the time varying systems work. Okay. Now, this time varying system has been in vogue for like decades. And normally what we have been, by we mean circuit design community, we have been using this in a pretty ad hoc manner, in the sense that we understand how an impulse train looks, we understand how convolution works, we'll just multiply and then see and then do everything in LTI domain. So that's how we have been operating for decades. But over the last 1 decade, I would say 5-10 years, there has been renewed interest in this time varying networks, because it seems like if we make a generalized time varying network, now depending upon how you make it, you can get a lot of things done with very minimal hardware. And hopefully by the end of this course, you will be able to appreciate that part, right? So that is the goal of from now to the end of this course. Okay, so for us to appreciate that, we need to understand, we need to develop a framework first, how to analyze time varying network, and then develop the intuition and then design something, right? So that's how we are going to go about doing it. And in that process, you are going to see that we'll come back to various other things that we have been talking about in the past. We'll go back to telegons again. We'll go back to some sort of reciprocity again. But all of these will be in the time varying domain. We'll go back to noise again, right? So, but everything in time varying domain. Okay. Okay, fine. So given hopefully that stage is set, so let's jump into how to go about analyzing these networks. I had sent out a video that kind of gives you an idea how to think about it. I will repeat some part of it for the sake of continuity, and then hopefully things will become much clearer. Okay, so let's assume we have an LTI network. This is a repetition of something that we had done a long time back, but in a slightly different manner. And it has an impulse response of ht. I apply a signal xt or VIT, let's say, and I get an output V0t. So what? Let me ask you, what do you understand? If let's say I am talking about the output only V0t, and I say that let's say I plot V0t. Tell me, what do you mean by this t here? T is time, but what time? Right, it's the observation time, right? Important thing to note, it's an observation time. Okay, so t is observation time. Okay, so which means that I have fixed myself a time in the time axis, and I'm going to sit there and I'm going to observe what the output is. Okay, okay, let me call this T0. And given that I know that a signal x of t or vi of t, any signal vi of t, I can break it down into slivers of impulses, right? So let's say I have a sliver of impulse here, which is at. So by the way, I am probably jumping ahead a bit. Instead of going to VIT directly, let me say that I have applied an impulse instead of VIT, I have applied an impulse here. Correct? So let's say this is VIT, an impulse here. Okay. And I have applied the impulse tau before my observation time. Right? Okay. So can you tell me what will I observe at T naught? Given that I know that impulse response is h of t or h of tau. Okay. So VIT is a delta pulse. VIT is a delta. VIP is an impulse that has been applied tau before T naught. Okay. So h of T naught minus tau. Okay. Any other comments? Okay, should be h of tau. You are saying it will be multiplication of impulse. VIT is impulse that has been applied here, wherever I have shown that tau before T naught. What is VIT? Okay, so it will be okay, one at a time. So let's Dhruv say first. VI is delta T. What? So how would you, okay, how would you, what is the definition of VIT here? Fine. So mathematically? T minus this, right? So which is? Fine. Okay. There was something else also that came from here. What will be the final output? Yeah, h of t minus T naught plus tau. Okay, so here basically I have chosen any arbitrary T naught. So I can basically say this is T, which is essentially what? Why did you say plus tau? Okay, okay. Which is h of tau. So these two are identical, right? So what about this guy? Is it correct? Incorrect? Correct. So h t naught minus tau or h t minus tau, if I, since I am generalizing for any t, is it correct or incorrect? So I have, under this situation, I have applied an impulse at that location. I am observing at t. So basically I have two options, right? I have option 1, option 2. Which one is correct? Both cannot be correct. Second one is correct. Why is the first one not correct? It's much simpler than that. Yeah, we're shifting time 2 times mathematically. What is the definition of h of t? What do you mean? Intuitively, what is meant by h of t or h of tau? What does tau mean in that h of tau? Let's say I say h of 3 second. What does 3 second mean? It's the time duration between when the impulse has been applied and when I'm observing. It's the difference of time between application and observation instant. Correct? What is the difference of time here? Tau. So your output should be h of tau. Correct? So it should be h of tau. You are going to see whatever h of tau. And it's one single value you are going to see. Right? That's what it means. Right? I'm sitting on a time cycle. I mean, you can think of that I'm sitting now at this point. Some event has happened 4 seconds back. I am trying to figure out the consequences of that event sitting now. So that's h of tau. It's a single voltage value, not a waveform. It's a voltage value. Fine? Okay. So the reason I'm spending time on this part is because it is slightly different from the way we had developed that convolution integral earlier. Okay, in the earlier development of the convolution integral, we focused on the impulse was applied and how the response of the impulse was conveyed through with respect to time, where observation time was not fixed. Here we started off with the observation time to be fixed, and you will understand why you are doing that. Okay, so now if I have to develop the same convolution integral using this methodology, what should I do? So instead, I understand that if I have a generalized VIT, I can break this VIT into impulses at various time instances before the observation time t. Correct? So I can basically say maybe I have a impulse here, and I'm interested again at time t. My observation time is t. Correct? I am now saying I'm trying to figure out what will be the response of this impulse, which has been applied tau before t. And then what will I do? I will simply move tau from 0 to infinity. Right? That will take care of all the effects from here to all the way there. Right? Fine. So that's the framework, right? So now what? So for that I need to find out the strength of this guy. So what is the strength of this guy? X of. So what is this distance or time? T minus tau. Correct. So this is x of t minus tau, and I have to multiply with the sliver, right? So that is d tau, right? And this is the strength of the impulse. What will be the effect of this impulse at the output? That strength will still be there as is, but it will be multiplied by some value, that impulse response. What will be that value? H of tau. Very good. H of tau, right? And then, so this is for one sliver. And then in order to find out the effect of the entire history, right? This is the history happening at that particular time instant, tau before the observation time t, right? But I am interested in the entire history, effect of the entire waveform. How is it affecting the observation at t, right? So for that, I have to integrate from tau equal to 0. Tau equal to 0 means this point, right? And then go all the way this side, that is tau equal to infinity. Correct? So this, your output hence will be x of t minus tau, h of tau, d tau, tau equal to 0 to infinity. Right? Yes.
Tell a bit more about putting in the strength of the impulse.
Okay. So if you recall, when we broke down any signal into slivers, right? So how did we find out the definition of this sliver? We basically said this is one unit step function. It's another unit step function. We subtracted, and then this limit tau tends to 0. So we ended up with an impulse, right? And what was the height of the impulse? And the height of the impulse was basically the value here times the width of the sliver, right? Delta tau. So that's what I have done there, right? So instead of again deriving the same thing, I basically took the value of the function at that particular point and multiplied with delta tau. Okay. Yes.
Putting in words, what we're doing is that at any observation time, we are seeing that whatever the impulse was at t minus tau, we are seeing what became of it from t minus tau till t, right?
Correct.
Yeah.
Correct. What became of it? I would say that what is the effect of it?
Yeah.
So, I mean, at a very philosophical level, we all are human beings. We are summation of our experiences that has happened from the day we are born, right? So we are kind of summation of the impulse responses. So it's basically that, right? So you can imagine each of impulse is an input that has happened to the system at some time, and we are finding out what is the effect at time t equal to some arbitrary time instant t. Okay. Okay, fine. Yes.
Mathematical equation in which tau goes from minus infinity to infinity.
Okay, so in this case, if I say tau goes from minus infinity, if tau goes negative, what does it mean? Means that I am anticipating something that has happened in the future to affect my present. It's a non-causal system, right? So not a physical system, at least till the time machines are there. So we're still good to go with t tau equal to 0. Okay, fine. So now before I proceed, another thing we should keep in mind is the fact that does it really matter where, I mean, does it really matter where the t is with respect to uh, this particular expression? I mean, what I mean by that is, so let's say I have chosen any arbitrary time t, correct? It really, so it could have been anywhere, okay? And I am saying that that's if the response of particular delta, wherever I apply, is h of tau, and that h of tau is independent of the choice of t, right? So what I mean is, so this might seem a bit redundant at present. Why am I harping on this? So let's say I chose to observe at t1, correct? This is v naught t. And let's say your VIT is an impulse which has been applied tau before. I'm going to get some value here. Another experiment I do where I point out another time t2 where I'm choosing to observe for the input that has been applied maybe tau before t2. What am I going to observe here? Same, right? So this and this will be identical. So as long as the difference between the observation time and the application of the impulse is same, my output is always same. Correct? So that is by definition LTI system is time invariant. The invariance means as long as I keep the difference between the observation time and the application time same, regardless of when I'm observing and when I'm applying, I will always get the same output, right? So that's the invariance. Okay, so now let's shift focus to see and to understand at least what's going to happen if this invariance is broken. And let's do it with one example. Let's say we have a RC circuit. This is VI. And let's say this R varies. Okay, so let's say this R varies and R is R of t. Okay, so this R of t, it goes from maybe a small value, let's say R1, to it doubles to 2R2, 2R1. Okay, with respect to t. So now let's say my observation time, let's say I choose to be here. I choose my t to be here. Okay, so I'm finding V naught is this. Okay, so how can I go about thinking about it? Now, if I compare with the LTI model where the value of R is constant, then what would I see? I would see that if I apply, let's say I draw the LTI equivalent here. So this is my time. So let's say I had applied an input tau before t. What would I have observed here? Say R, let's say C. What would I have observed? The value that I will observe here will be 1 by RC e power minus tau by RC. Very good. Right? If I had chosen to observe it here, for an input, again, that is applied tau before, I would have gone the same value, right? I would have gotten 1 over RC e to the power minus tau by RC. Correct? Now let's switch focus on the top. I am observing here, and let's say the input has been applied here, tau before. So what should I observe? 1 by 2 R1C e power minus tau by RC, if this difference is tau, right? 2 RC, correct, 2 R1C. But let's say my observation time was here, and I had applied an impulse here, but this is the same tau. What would I have observed? Slightly higher value, because R1 is R1 is larger, smaller. So this will be 1 by R1C e to the power minus tau by R1C. Correct? So essentially what we are seeing is your impulse response is not constant when your system is time varying. Right? So this should be intuitive, because if the system itself changes, why should we expect impulse response, which is a property of the system, to change, to be constant? Right? So if the system, you can think of it, it's a combination of two systems in which at some point of time the R was R1, and other points of time the R is 2R1. So a combination of R1 and C is going to have some sort of impulse response. A combination of 2R1 and C are going to have different types of impulse response. Right? So it makes sense intuitively also to appreciate the fact that your impulse responses will not be the same even if I keep that distance between observation time and the application of the impulse time constant, because it now depends on not only on the difference, it also depends where you are observing. Right? Make sense? So it becomes a two-variable system. An LTI system is a single variable system, where we have to only keep track of the difference of the application time and the observation time. In an LTV system, you have to keep track of where you are observing also, on top of the difference between the observation and the application. Correct? So that is another fundamental difference between LTI and LTV. Right? So key takeaway is, must keep track of in addition to the difference okay, fine. So which means that I have to figure out in this if I have to do for this particular case, I have to figure out the impulse responses for both scenarios and then proceed with analysis. Right? Okay, so let's do that. So there is, by the way, there is a nomenclature for this. The nomenclature is, which means that I cannot use h of tau anymore. I have to have two variables to take care. So that's why we call this h of t where, so obviously h is the impulse response. This time, this t is the observation time. And tau, comma tau, this two variable, tau is the difference between the time at which the impulse has been applied and t. So basically the impulse has been applied at time delta t minus tau, right? So the impulse has been applied at t minus tau. Fine. So let's do it for the time varying RC circuit. So let's say that this was R and it jumped to 2R. After some time t naught. Okay. And I need to develop a framework in which if I apply any arbitrary signal, correct? If I apply any arbitrary signal, I should be able to find out the exact response at any time t. Correct? So for that, what do I need to know? What is the first thing that I need to know about the system? We need to know the impulse response. Correct? So now, can you intuitively tell me how many impulse responses do I need to know? 2, right? One for time t greater than t naught, another for time less than t naught. If I know these two, I should be able to accurately characterize my system without any problem. Correct? So, which means that, so firstly then, let me just write it down. Need to find ht of tau for t greater than t naught, greater than equal to, or t less than t naught, not or, and t less than t naught. Right? Note that I'm stressing on the fact that we are interested in the regions corresponding to t, not tau. Correct? We are the regions are with corresponding to t, not tau. Okay. Even though it's obvious, sometimes it gets messy in the head if you are not paying close attention. Okay, fine. So when we say that we need to find ht of tau for these two regions, which means that I have to fix my observation time for each of these two regions separately, do two separate experiments, and I'm going to get two separate results. Correct? So which is the easier thing to do? Where should I fix my observation time first? So the easier one, t less than t naught, right? So because I mean, time flows from left to right. So if I am observing before any change has happened, then it's for all practical purposes in an LTI system, right? So it's easier to do. So I'll do that. So let's say this is h t, where t less than t naught tau. Okay. So I should not write it on the same thing. I'll write it here. H t less than t naught tau, because h I'll be plotting with respect to tau. Right? Because h is always with respect to tau, but here the t is a variable, t is a parameter. Correct? T is a parameter, so but the x-axis for h will be tau. Right? Okay. So now my observation instant is here. Sorry, not there. T less than 10 naught, right? So this is my observation instant. This is some arbitrary time t, and I am applying an impulse on this side, right? So I choose a point, any point tau before this t, where I have applied the impulse, and I'm interested in finding out the output at time t. What will that output be? Simple. Tell me. 1 by RC e power minus tau by RC, right? So your h of t minus t, h t less than t naught tau is the same as whatever we knew earlier. So it will be simply be this. No complication, correct? There is no effect of t at all, which makes sense because the system hasn't changed, right? So there should not be any effect of t, okay? Or there should not be any effect of t naught, I should say, right? Okay, so now let's come to the more interesting part, where if I have to find out h t greater than equal to t naught, or this is also less than equal to is fine, right? So I can simply say h t greater than t naught tau, and both should kind of converge. So this we have to find out, which means that my system is, I am now sitting at a time greater than t naught, correct? And I am interested in finding out the response for any arbitrary time t, right? That has been for any arbitrary time tau that has been applied before this t, correct? Okay. So let's do that. So if I apply an impulse here, let's say, correct? So again, okay, so this will again be, this can, I can subdivide this into two categories, right? In which the impulse has been applied in this region, correct? If the impulse has been applied in this region, it is only going to see a time constant which is 2RC. Do you agree or? Okay. But if the impulse has been applied here, it is going to see the time constant of RC for some time, and then 2RC for the rest of the times. Okay. Okay. Fine. So that's all right. So if I say that, let's do the general case first, where the impulse has been applied somewhere here, encompassing both the periods. So let's say that I call this tau. So how would I go about analyzing this? So yeah, so I have applied it here, right? So what will be V naught? What will I observe at t? So how will you go about thinking about it? No, right? So see, I mean, the impulse has been applied after time before. Okay, so impulse has been applied here, right? So once you apply the impulse, what will it see? It will see a RC, where R is R and C is C, right? So, and it is going to decay, right? And then it will hit that when it hit the time instant t naught, and then the next evolution will start. But till t naught, it is seeing an RC, correct? So how will it evolve? 1 by RC e power minus that, exactly, right? So it is going to evolve, output is going to evolve, and you are going to observe something like this, where this value will be what? One by RC e power minus this distance No, right?
T naught.
See, this is T naught. Okay. So let's see. So this is T. This is T naught. And this is tau. Correct? So what is this then?
T minus tau.
So what is this part? T minus tau. What is this part? So this will be T naught minus T minus tau. Correct? So the value of this this decay, after the decayed value, this will be 1 over RC e power minus of T naught minus T plus tau. Correct? By RC. Correct? So then it is going to evolve, then it is going to see the 2RC decay. Correct? So when it's going to see a 2RC decay, now this serves as the initial condition on the capacitor, right? The initial condition on the capacitor that is going to decay with a time constant of 2RC, right? So whatever this is, times e to power minus this distance, T minus T naught over RC, right? By 2RC, correct. So essentially I'm going to see this will be 1 over RC e power minus times e power minus T minus T naught by 2RC. Correct?
In both the case, like T greater than T naught and T less than T naught, tau will be different, right? We are taking a tau as a one time instant.
Yes. No, tau is not the time instant. Tau is the difference between the observation time and the application time.
Until that will be
Not necessary, right? Why do you say that? I'm applied an impulse and I'm observing, or I'm observing for the effect that has happened tau before. So in one case, I am observing in this region. In one case, I'm observing in this region. I can, let's say I'm observing 1 second before my observation time, right? So that my observation instant can be here, or my observation instant can be here. But that 1 second is 1 second, then 1 second is the tau. Correct.
time, like certain time also RC and 2RC.
Yeah, the tau is getting like mixed with the time constant of the cell.
Oh, tau is not time constant. Sorry. Okay. Okay. Yeah. Yeah. Maybe I should have cleared it up earlier also. This tau is not time constant. Okay. Yeah. I don't know. So in the literature, we call it tau. I stick to tau, but this tau is not time constant. Sorry if I have confused you. Yeah. Yeah. It didn't occur to me also that can be confusing. Correct. Okay. By the way, was that a source of confusion for anybody else? Okay, fine. Okay, so we have, so far so good? Okay, how much time we have? Okay, about 10 minutes. So this is, so we have, this is also, by the way, I mean, we have some constant times e power minus t over something, right? So if I mark it out, so this becomes 1 by RC. You have this e power minus t0, and this is also e power plus t minus t0 by RC times e power minus tau by RC. times minus t0 by 2RC. Correct? Did I make a mistake somewhere? No, this is fine. So you have 1 over RC e power t minus t0 by 2RC times e to the power minus tau by RC. Okay. So this is the condition. This is again this exponential decay, but it decays from a different value. And that value is a function of t. Correct? And you see that now the effect of time variance is coming into picture. In the earlier case, it was not a function of t. Here, it was h of t minus tau was not a function of t. H of t comma tau was not a function of t, because around the time I'm observing, nothing has changed. Here, around the time I'm observing, something has changed, and hence it makes sense that it will also be a function of time. Okay. The third part that we did not consider till now, that's the easy part, we should now consider, is the fact that here we assume that tau has been applied before tau, this impulse has been applied before the system has changed. But that is the assumption on tau is greater than t minus t naught. Correct? Tau is greater than t minus t naught. But there is another case in which tau is less than t minus t naught. Right? For that case, so h of t comma tau, where tau is less than t minus t naught, but t condition remains the same, t greater than t naught. So this is simple. This is 1 over 2RC e power minus tau by 2RC. Okay. So now you have three things to deal with. So now this is for, so now what have we figured out? We have figured out that if we are observing, I don't think we have time to get into the generalized thing, so we can maybe talk about this and take questions. We have figured out the fact that if we are observing anything before t naught, we don't have to worry too much about anything. It's equivalent to how we are doing LTI system. That is region 1. Now, if you are observing anything after t greater than t naught, right? So then we have to be cognizant of the fact that if the impulse has been applied before the system has changed or after the system has changed. Correct? Now, given the fact that your input is continuous for all time, correct? So this is VIT, and let's say this is my observation time t, and let's say your system has changed here, correct? Which means that you have to be bothered about whether, I need another color, this one. Okay. So you have to be bothered about when I am breaking this this waveform into train of impulses. These impulses some of them have been applied before the system has changed. Some of them have been applied after the system has changed till the time of observation. Correct? So for all of these guys, okay, your impulse response will be similar to this. For all of these guys, your impulse response will be corresponding to this. This is for the case when t is greater than t naught, right? And you have to do another calculation in which your t is less than t naught. Your input in this case is, you don't have to bother about anything that is happening after t. So which means that For all these cases, it's equivalent to that first impulse response. That is 1 over RC e power minus tau by RC, right? So once you have that, then you do convolution integral, assuming appropriate limits for each of them, right? And the final output that you get is essentially your total, is your eventual output, okay? And when you talk about the impulse response, or rather, I should not say impulse response now. When we talk about the sinusoidal steady-state response, sinusoidal steady-state response in an LTI system is equivalent to saying what is the response to an input when a complex input is a complex exponential e power j omega t, right? Remember that? Okay. So similarly, for an LTV system also, we need to find out what is the response when an input is e power j omega t. Correct? So just like in an LTI system, when I applied e power j omega t, I had got something which is h of j omega times e to the j omega t. In an LTV system, when I am applying e power j omega t, I'm going to get something. What is that something? That I'll be more interested in, right? So for example, I know that LTV system is characterized by ht comma tau, right? So in a generic sense, I can basically say this is equivalent to your V naught t. So here, what was the expression? It was a convolution integral, which is h of. Okay, let's not do that now because it will. I don't want to write it down. I want to derive it. I think we derived. Did I derive it in that lecture that I provided? Okay, fine. So then, can you tell me what will be this? How did it come? Okay. So yeah. So ultimately, so the key thing to note is that this h of j omega, this is independent of time, independent of observation time, independent of t. Here, if I do, I'm going to get comma t to the power j omega t, right? So this is the envelope which is dependent on time, right? Intuitively, that should make sense because when I'm applying a sinusoid, right? So for certain period of time, it is seeing RC. For other periods of time, it is seeing 2RC. Correct? So which means that, so this is where the system changed from R to 2R. Your output will be some till this T naught at steady state, there will be some waveform. And what will be the envelope? For RC, what is the amplitude? This is Vp sine omega naught t, let's say. So what will be the amplitude of the waveform that you're going to see at steady state across C? Yeah, right. So it's basically Vp by under root 1 plus omega square r square c square. And there will be a phase shift, right? And after t equal to infinity, what are you going to observe? Right. So it will be smaller amplitude or higher amplitude? Smaller amplitude. So you're going to observe at t equal to infinity, you're going to have the smaller amplitude. Note that this amplitude is not changing, right? At steady state. Right? That's the envelope. So that is h of j omega. Okay. But somewhere in between, when the system changes, this amplitude will go from high to low. Right? So if I just draw the envelope, so it will go from high to somewhere low. If I'm interested in what is happening here, then I have to find out this guy. right? The effect of time information is in this intermediate zone. I do not have to bother about time information if I am at steady state on either side. Okay, and that is why we need to evaluate h j omega t properly. Now things get even more interesting when this is periodic, right? Here it seems like I have changed and kept it as is, but if it changes every periodic instant of time, every periodic time interval, then you see that it probably, this type of framework probably might be too messy to deal with. I mean, how many intervals am I going to calculate this for, right? So that is something, when things become periodic, the analysis, even though it might seem it becomes tricky, in a certain way it becomes simpler, because moment you have periodicity, you think Fourier series. We have a framework to use that, and we are going to use that, right? So in the next class, we will derive this particular thing in a brute force method. It's instructive to do it at least once. Then we'll go to that periodic stuff. Okay. Okay. Stop here. Yes.
Yeah, yeah. So like, is it in this blue, is it technically correct to say that when the resistor shift from R to 2R, your impulse response, you're seeing your what becomes of your impulse response after the 2 tau time shift from that particular moment till the observation time? Because when you simplify it, you'll be having T minus T naught minus 4 times tau.
I didn't understand why 2 tau. Where from 2 tau come from? So what are you replacing 2 RC with? 2 RC is not tau, right? Hold on.